So, welcome. Let's give some time, a couple of minutes, to welcome more participants. Actually, we had around 60 registration. So let's see how many people out of them will be participating in the meeting. Good. I think we can start. So, hello everybody. Welcome to my talk, which is about the application of topology design optimization in structural acoustics. I am Dr. Mustafa Ranjba. I'm leading a group which are doing research on bio-inspired mechanical metamaterials in the Department of Mechanical Engineering of Ankara İlmi Beyazıt University in Turkey. And yeah, more about me actually. I have a master's degree in structural vibration monitoring. I had the honor to work with Professor Dr. Siamak Ismailzadeh Khadem. He passed away unfortunately last year due to the cancer. He was an international expert in the field of structural health monitoring vibration signature analysis. I have some industrial experience in automotive sector in Iran. I have the honor to be the PhD student of Professor Stefan Marburg, who is an international expert in the field of vibration, vibro-acoustic and acoustic. He's leading the chair of vibro-acoustic in the Technical University of Munich. So I learned the basic of vibro-acoustic from him. I have done some research on structural acoustic and topology optimization of metal shell during my PhD thesis, mainly in the decade between 2003 until 2013. Then I had a chance to work for a couple of years in collaboration with Professor David Herring from the University of Kentucky over the design of mufflers and silencer. And then I started to work on the vibro-acoustic design of a structure with negative Poisson ratio in collaboration with Professor Fabrizio Scarpa in the University of Bristol. I'm working on Auxetic structure with negative Poisson ratio. But in parallel, I have tried to also expand the knowledge of vibro-acoustic among the students by teaching the courses which are suitable for undergraduate, graduate students, also vibro-acoustic vibration, engineering acoustics, advanced mechanical vibration courses for different level of students. And also, in parallel, I try to expand my international cooperation with various researchers and also offering workshops so that we can expand this area from theory, from research point of view, and also industrial collaboration. Also, I have offered several keynote talks regarding this topic. Also, I am the founder and scientific chairman of the International Conference on Advanced in Mechanical and Mechatronic Engineering. We had very well-known keynote speakers in our conference, and it was our honor to host them. And we had very high-tech meeting discussion. Unfortunately, due to the pandemic, we couldn't continue it. So if I want to discuss about my experience, actually I can divide my works on structural acoustics and engineering acoustics in 3 branches. The first one was the topology design optimization of the metal shells with respect to their vibro-acoustic performance. The second branch was the acoustic design of muffler and silencer. And the third branch, which I'm currently now actively working on it, is the vibro-acoustic design of metamaterial structure with negative Poisson ratio. So if I want to show you a brief history about the publication that we had about, for example, the topology design optimization in structural acoustic of metal shell structure. So we started to publish in 2010. It was about finding the best design within limited time. It was about the comparative study among the optimization methods in structural acoustic. So I had the honor to work with Professor Hartke, Denny Fritze, and Professor Marburg. My PhD thesis was in 2011 about this topic again. And we published more paper in this area regarding using of hybrid optimization, optimization techniques for reduction of the optimization time and improving the accuracy of the design. Another publication appeared in 2012. It was about application of taboo search method in structural acoustic design of plate. Also more methods regarding like using of the genetic algorithm, random search method, usage of artificial neural networks actually, because in 2013 we had the idea to use the artificial neural networks or neural networks for making fast approximation and reducing the computation time for structural acoustic designs. We did. I had some master student when I was working in Cyprus, and we worked also on the sensitivity analysis of our application of artificial neural network in structural acoustics. And finally, the last publication was about the theoretical and experimental investigation of acoustic performance on multi-chamber reactive silence. So, so if you want to start the theory about the optimization in structural acoustics, so I may cite the work of Coleman, which is about the basics of the acoustic of machine. So here we go. Actually, a very reliable and well-known measure for the noise emitted from the structure is the level of radiated sound power. So, which is a function of the circular frequency. Here, actually, if you consider the level of sound power with respect to a standardized value, we can write it the equation number 1, which is a logarithmic scale of the sound power. And then we can write the sound power in terms of the air impedance and the radiating surface and the normal velocity of the surface of the structure in terms of the circular frequencies in the radiation efficiency. Then we can here explain the transmission impedance as a function of the square of the surface velocity of the structure over the square of the excitation force. So if we substitute the equation of 3 in 2, we can have the equation number 4. And then here we can write it as a level notation. We can reach to equation number 5, which represent the level of radiated sound from this from one structure, which can be a combination of the summation of the resulted from the radiation efficiency, from the structural board sound, and from the excitation force. Here, I should say that it is a complicated combination between these two levels, because if you reduce one of them, it can cause that we are increasing another one. But if we want to simplify this equation, we know that there is an upper end for the radiation efficiency. Therefore, the level of noise due to the radiation efficiency is bounded. And here we can pay also for the force. So we can say that if we concentrate on the structural bone noise, then we can have a representative value for the radiated sound from the structure in an easier manner and faster manner. So here we can say that the level of a structure bone sound can be defined by the equation number 6. And if you want to make a root mean square of these parameter over a wide frequency range, then we can use the equation number 7. Although it is not exactly representing the radiated noise from the structure, but it is a representative value so that you can have a feeling about the radiated noise from the structure. So the trend are same, but maybe the values are a little bit higher. So having this equation number 7, if you want to minimize it over a specific range for the design variables, then we should use the, we should go through this flowchart. So after initialization of your finite element design, you can go through the calculation of the objective function, and here you need to use different optimization algorithm. We will discuss about the different optimization algorithm. Maybe you need some approximation. It depends on your type of optimization algorithm that you will use. We'll discuss about them. Then you go through the convergence check and see whether the loop will be terminated or not. To show you how difficult it is to find an optimum design, let's discuss about this function which has only one design variable. So having this objective function in one dimension, you can see that we have several local and global minima. And in some area, even we have plateau. So in this case, we know how is the objective function, but in the reality, in structural acoustic application, we don't know how is the objective function. Really finding the optimum design in a structural acoustic application is like catching a black cat in a dark room. So because we have no idea about the shape of the objective function. So here, actually, you can see that if you start from different point and using, for example, a specific gradient-based method, maybe you can just find the nearest design. So maybe you need to change your optimization technique. So if you see another objective function in 3 dimensions, you see how nonlinear is that objective function, and therefore finding the best design is really difficult. And the objective function normally in structural acoustic are normally also highly nonlinear. So we have problem regarding the usage of second order optimization techniques because the objective function will not be convex. And we should consider to investigate the whole of design space on a uniform manner so that we do not miss some areas of the design space. So here you see that we should have a specific approach for searching the design of space. So here we need to deal with different optimization and approximation methods. So some of them actually can provide a good convergence speed. Some of them are more accurate. Robustness is another issue. So what I'm showing is from my PhD thesis from 2011. We consider different optimization techniques, whether they were stochastic or non-stochastic or gradient-based method. So so the methods are written here like simulated annealing, method of feasible direction, method of moving asymptotes, sequential quadratic programming, long memory, Broadband, Gordon-Shanoff for bound constraint methods, application, Newton methods, simplex methods. So combination of simulated annealing with neural network as a hybrid technique, genetic algorithm, method of moving, mid-range multi-point techniques, control random search. So we see each of these optimization techniques, they have a different mathematical background. So you should know how these techniques they are working. One of these techniques can move even upward, like simulated annealing. Most of them, they are searching the area in the vicinity of the initial design. So some of them, they are searching the whole of design space. The number of objective function evaluation for each technique is different. That means different time cost that you have to pay for the optimization. So also we consider different approximation techniques like a global method using neural network, design of experiment, some mid-range method actually like single point, multi-point, and local approximation. So we had the impression that some of the method can work very good regarding the optimization time, like method of moving asymptote, which is a very powerful technique, which is providing a convex approximation of the objective function at each iteration. Therefore, you are be granted that you will find an optimum at each iteration. So regarding, we had some categorization regarding the speed of the optimization. It is important because in structural acoustic, the calculation is quite time consuming. So the case study for our research in that time was one, let's say, plate, 1 by 1 meter with a thickness of 1 millimeter made from steel. So the concept was to use the topology optimization, or let's say modification, by considering 9 design variables over the surface of the plate, so that when they are changing statically, the shape of the plate is changing, and this change in the shape of the plate actually can affect the stiffness of the structure, therefore affecting the surface displacement and surface velocity under different type of excitation. So here you can see that the level of structure born for the original flat rectangular plate over the frequency range of the 0 to 100 Hertz. This is the frequency range that we consider for automotive application. Normally for automotive application, normally the interested frequency range is is about 200 Hertz, 1/3 octave band. That means between 170 to 213. Anyway, we consider a low frequency range for our application. So here you can see that for the rectangular plate, the radiated, the root mean square level of the radiated sound power or the frequency range of the 0 to 100 is about 45.31 decibel. The mass is here given. So the initial fundamental frequency is provided and the maximum level of sound. So you see that by doing an initial, let's say, modification here, you see initial modification. The modification had been restricted between the -10 to 10 millimeters, so that to meet the manufacturing, real manufacturing restriction for the manufacturing of a plate with 1 millimeter, for pressing a plate with 1 millimeter thickness. So you see that we had some reduction in the radiated sound. And by using different optimization technique, I'm showing the base design. Here you can see that how for example, in the dark area, we had a positive change in the, let's say, the surface height of the plate. In the other areas, we have the negative, let's say, downward modification in the plate. So this design, actually, they are providing good opportunity. This type of passive noise control method is not changing the weight of the structure, the mass of the structure. So without adding the mass of a structure, by changing the local topology, okay, the local topology, you can affect its radiated sound properties. This is the concept, the topology optimization. Here we are changing the outer surface of the structure For muffler, we are changing the internal of the muffler geometry. And for metamaterial, we are changing also the internal structure. So this concept can be useful for reduction of the radiated noise from the structure. So this is the result of the paper from 2010. So here you can see that the topology optimization speed rate, actually they are actually you can see that we had the best, let's say, the best improvement at the initial, let's say, calculation. By increasing the number of calculations, you couldn't reach more. So that means the best gain have been reached at the initial computation. And we realized that the rate of success for different type of optimization methods are different. So that means by increasing the number of computation, how you can reach to more gain in the reduction of the radiated noise. And here you can see that by using of different optimization techniques, we are reaching to different optimum design. So that's why the objective function in structural acoustic design is quite nonlinear. So we have several optimum design. For example, by method of feasible direction, which is gradient-based technique. So you can see that this is the flat plate, the solid line. This dashed line is the initial design, and this is the optimized design. You see that after spending a specific number of calculation, let's say 500 function evaluation, we could shift the first peak to a higher value and also generally reduce the level of structure-borne noise. By different techniques like sequential coded program, which is a second order method using the Hessian matrix, we could have better improvement, but you will see that actually some of the method could provide a good design, but orally they couldn't provide, I mean, for different initial design, they couldn't provide a good result. So it is a matter of robustness, base design, and computation time, especially for highly nonlinear application. Here you can see for method of moving asymptote, you see that the shape, the optimum shape is quite different here, and you have a very nice result over a wide frequency range regarding the radiation reduction of the radiated node. This doesn't mean that in the reality, if you produce this result, want to verify the result experimentally, you can reach to, for example, 20 decibel reduction. No, even a 1 decibel reduction is a quite big success. Just it provides the idea that by how you can change the geometry of the shell plate so that you can reduce the radiated noise according to the type of excitation. When you have non-symmetric excitation, the shape of boundary condition, etc. Here you can see the result from mid-range multi-point method. So also we use the hybrid topology optimization technique in 2012. We use a hybrid design of experiment technique. It was also quite useful. We used tabu search technique, which was published in 2012. It shows that by tabu search method, for initial design, we can reduce up to around 15 decibel in the radiated noise. And we were almost in the between of the allowable range for the design variables without changing the mass. So for other techniques like genetic algorithm, control random search method for hybrid neural network, you can see we have different design, but each of them, they could, for example, for genetic algorithm, we could have very nice result over the whole of frequency range, and you can see the different geometries, the result, optimization result. So it is quite important. They are published in different papers, our papers, across the different years. So now we are shifting to other branch. Actually, I had the idea that actually by using the topology optimization, we can affect the vibro-acoustic performance of the structure. That was a begin after it began for a long research collaboration with Professor Fabrizio Scarpa, because he introduced the field of Auxetic to me and told me that by changing the Auxetic geometry, we can also changing the noise radiation. So we emerged in this field and we published a lot actually. A couple of my PhD students graduated, several master students graduated. So, for example, here you can see the representative publication starting from 2016. We started with Vibro-acoustic optimization of anti-tetrachiral and auxetic hexagonal sandwich panel with gradient geometry. We published another paper in 2018. It was about the Vibro-acoustic design of auxetic hexagonal honeycomb structure. In 2020, we had another paper about vibro-acoustic analysis and topology optimization anti-tetrachiral auxetic lattice. And in 2020, we developed the application of auxetic structure for enhancement of the energy harvesting. And applied acoustic, we had a recent paper regarding the vibro-acoustic performance of anti-tetrachiral auxetic sandwich panel using local resonator. And another paper recently published in thin wall structure. It was about novel cross-shaped phononic crystal and broadband vibration wave attenuation. And another conference paper in 2021. So the concept of Auxetic says that you need to deal with a structure with negative Poisson ratio. So what does it mean, the negative Poisson ratio? That means when it is acting in reverse of the normal material. That means when it is under tension, it is contracting laterally. So this is not a matter of the material properties of the structure, but it is a matter of geometry of a structure. That means you can develop a structure with negative Poisson ratio with the same material, but with changing the internal geometry of the structure. So the auxetic structure are either cellular, like conventional, like actually cellular. So if you consider conventional honeycomb, if you change the internal angle, then you can produce auxetic structure. And you can also develop random network auxetic structure that are mainly inspired from the nature. So actually the auxetics, they have the ratio in the history. So also in the nature, if you can see in the nature, in the leaf, actually, in the animals, the different animals, actually in the trees, you can see auxetic structure. They are cellular, lightweight, and quite good in terms of the impact, noise radiation, low density. So due to the cellular structure, they are easy to produce. And specifically for bending, for the case that the bending within the structure is important, so they can perform very well. The bending is important because the bending is an issue in vibro-acoustic as well. They are repetitive and cellular. So you can see many historical buildings that they have used this type of the concept from many years ago. Also in the Islamic patterns, you can find a lot of similar auxetic pattern. So if I want to show you how the geometry of one structure is changing and affecting the radiated noise, you can see it here. It is the result of our paper in 2016. And you can see that for one hexagonal cell, when the internal angles are positive, then you have a classical honeycomb structure. So for classical honeycomb structure, we can reach to a specific amount of the radiated noise. But when we change the internal angle, okay, we can reduce the level of radiated noise. That is very interesting to show. And for one antitetrahedral structure, here you can see that how when we are changing the internal, let's say, radiuses, internal radius of the cylinders of one antitetrahedral structure, how you can reduce the radiated noise from the structure. This is important. We are not changing the material, we are not changing the mass, okay, just by changing the internal geometry. So this is an advantage in comparison with the composite material. In composite material, you need to change the material, then you need to go very complex production, manufacturing approach. But here, just you're using one material, although you can use different material as well here. But with one material, just changing the internal geometry, you can develop quite a structure. This is useful in aerospace application, because in aerospace application, you cannot change the outer surface of the structure because it can happen that it is affecting the aerodynamic performance of the structure. But internally, you can change it. And this is exactly the point that you can use the Auxetic structure for Vibro-acoustic application. They have shown very good performance for aerospace applications. So these are the result of our paper. So here you should decide which Auxetic pattern you want to use. Then, according to your Auxetic pattern, whether you are using one exact modeling or homogenized modeling. So the homogenization here is useful for increasing the convergence speed. Actually, I had the honor to give a talk about the application of the homogenization in modeling of the metamaterial for Vibro-acoustic application almost 2 days ago in UK Metamaterial Network. It was a very fruitful discussion. Maybe if you want, you can reach to that videos as well. But here we are continuing. So either you are using either exact modeling or homogenized modeling. Then you go to model verification and optimization and go on. So let's start with our example. If you remember, in my PhD thesis, I worked on one plate. You remember? Yeah, it was a plate 1 by 1 meter. Okay. So here we go. We continue that concept actually. Once again, the type of excitation here, if you see the dash areas, are the type excitation from my PhD thesis. So why we did that type of excitation? Because we wanted to excite the most of the modes over the frequency range that we are considering. And therefore, we consider one non-symmetrical loading over the structure. And after having a short meeting with Professor Simon Nile in the University of Bristol, he proposed me to change the direction of the excitation to see how is when we change the direction of the excitation. Therefore, this case was produced as well. And here you can see that we have used one antitetrahedral core for the sandwich panel instead of using a typical solid shell plate. And we used this core and we investigated its vibroacoustic performance. So here I should say that we use also the homogenization. The homogenization was quite useful here because it could reduce the computation time and we could verify the model, that homogenization model is working well. So here you can see the homogenized sample by doing a sensitivity analysis or the type of the element that were useful for the modeling. And here you can see that this is the original model with initial cell radius of 4 millimeter. That means for all of the cell, we have one same initial cell radius. And then here the dashed line, the gray one, is the optimum cell radius and optimized thickness. And the red one is optimum thickness with initial cell radius of 4 millimeter. So you see that then here we have considered a concept of the gradient geometry. That means we consider 5 bands so that in each band we can have different cell radiuses. This concept coming from the nature, if you have a look into the palm trees, you see that the palm trees normally they are in the coastline. And on the coastline, actually, you have always the wind, and they are always resisting the wind. So they are always under bending. So the internal mechanism within them is helping them to sustain the bending, and the bending is important in vibro-acoustic. And you can see here that, for example, this is for antitetrahedral. Here is for the hexagonal case. You can see that how the hexagonal case, when we are using the hexagonal case in the gradient geometry, when we are changing their internal angles, we can reduce the level of noise, changing the natural frequencies of the initial structure. So you see the effect of the optimization of the geometry of oxidate structure on the vibro-acoustic performance of the sandwich panel. In another paper in 2018 in composite structure, that was the result of my PhD student, Dr. Mohammad Sadegh Mazloumi. So we used in another format the concept of the gradient geometry. So here we consider 9 design areas, so that at each design area we can change the internal angle of an auxetic cell. So you can see how is looking the internal geometry. So please keep an eye on this figure, because I will show that how we have developed it over the years. I will show you that another of my PhD students considered a full gradient geometry optimization for this case. And so this is like a chain. And here you can see that actually, if I want to discuss for a sandwich panel, if the core is a uniform conventional hexagonal topology with a constant angle of the 30 degree, the mass is given and the radiated level of noise is given around 127. So if we consider the same dimension but with lower thickness, but here the core is filled with the same material. That means the core is not cellular anymore. So you see that actually the level of radiated noise is increasing. But if we consider the same structure, okay, the same structure, I mean with the like case 1, with field the same, I mean if you consider a solid structure like the case 1, so you see that we have increased almost 4 times the mass, and also, but a little bit reduced the noise. So here you can see that the effect of the reduction of the mass and the radiated noise in the same time. Also again, here you can see in another table the effect of the reduction of the mass in parallel with the reduction of the noise. In another table here, you can see that we have reached a different design by different optimization techniques, by a little bit change in the mass of the structure and a very good result in radiated noise. Good. In another paper, actually, we discuss about the application of the genetic algorithm in reduction of the radiated noise. Here you can see that how the optimum design actually could provide a little bit improvement around 1 decibel in the radiated noise from the structure and shifting the peaks to higher frequency range. So here, actually, after graduation of my PhD student, I had always the question that, okay, so what we consider in our case, it was always a harmonic excitation, but non-symmetric over the surface of the plate. How about if we have different type of excitation, like white noise, pink noise, Brownian, blue, violet noise, but in the same areas that they have been applied from the previous cases. And I wanted to see how is the effect of different loading. Different loading and also different boundary condition, because different loading mean different application in engineering. And different boundary condition can affect the wave propagation across the structure, because when the boundary condition is changing, the way that the wave is reflecting after reaching to the boundary is different. So we investigated different boundary conditions like simply supported, clamp condition, mixed boundary conditions, simply supported clamp condition by different excitation case. And here you can see, this is the result of our paper in Journal of Structural Stability and Dynamics in 2020. You can see that how different noises, they are producing different radiated noise, and how the boundary condition can affect. So you can see that the clamp condition, they are radiating less noise. So the simply supported providing more noise. Another application that we developed, it was in a dynamic application for enhancement of the energy harvesting from piezoelectrics by using the Auxetic, so that we could enhance the let's say the energy from the surface velocities of the structure by using one Auxetic implant. Another paper in 2021, we had the idea, okay, when we use the tetrahedral structure, we have some cylinder. This cylinder can be used. In some previous work by Fabrizio Scarpa, they filled it with rubber metal material. So they had the idea, okay, similar idea actually, how we can use this cylinder as a resonator. So, as a local resonator. And how about if we optimize the mass actually, and let's say across this resonator, let's say cylinder, so that we can affect the vibro-acoustic performance of the sandwich panel. Whether, for example, how we can reduce the level of noise at a specific frequency, so that we can adjust by using local resonator to reduce the level of noise at a specific frequency, like this figure 13. Okay, so we use once again here the method of moving asymptotes by different, let's say, areas, 9 design area, 9 region, 36 regions, so that we could reach a very good improvement in the reduction of the radiated noise from the structure. So another idea I told you about the bending. So if you look at the old historical building, they had the idea to use this type of stepwise structure to carry the load of the roof. So because in that time they were metal. That is the idea that I had to use for a stepwise Auxetic structure. And for in-plane and out-of-plane performance. And that was the subject of one of my master students. And we realized that by using this type of stepwise structure, for in-plane and out-of-plane, we can have very good reduction in the radiated noise. For example, for out-of-plane structure, when we are using layered Auxetic cell, hexagonal cell, we can, by using layer Auxetic structure, by specific design, we can have very low level of radiated noise because we are changing their stiffness, and therefore we can have a better noise radiation property. That was a subject of one paper that we published recently in collaboration with Dr. Farang Dus from Florida University and Dr. Anastasia Kroshinka from the University of Groningen. And another paper from one of my PhD students, Dr. Ali Hossein Khani and Dr. Mr. Panai and Dr. Khan Sanami. We use the Auxetic patterns for broadband vibration attenuation. And we designed them novel Auxetic patterns Actually, they are, we could find them in, let's say, Iranian and Islamic pattern. So we developed, printed them, and tested them, and they could show very novel performance in filtering the propagating waves over the various frequencies. So here you can see that without filtration, how is the frequency response function of the structure? So if we use 2 layers, how is the reduction in the frequency response function? And for 3 layers and 4 layers, we could actually we could have some stop bands in the transmitted vibration frequencies. We had another also result in our paper in 2021, and we use also gradient topology optimization for antithetical structure. So here you can see that the initial design with the same, let's say, internal radius for all of the cells. Then we had genetic optimization. Also, we compared with method of moving asymptote. So genetic optimization is a global optimization technique. Method of moving asymptote is a local optimization technique. So their nature are different. Method of moving asymptote is actually looking downward after making approximation from the objective function and finding the minimum by gradient search. But the genetic algorithm is different. So the time that you need to spend for genetic algorithm is different because it is searching the whole of design space with the method of moving asymptote. But you see that the results are not too much different. So that's the experience that I want to show you, that if you use suitable, let's say, appropriate optimization techniques, then you can have a good result in a short period of time, which are relatively reliable. Also, we did some hybrid technique. Actually, the initial idea from the hybrid technique came from when I was a PhD student in Dresden. And we had a discussion, I had a discussion with Professor Marburg, and he had the idea to start from a global search, like genetic algorithm, and finding most promising areas and then focusing on that areas by a good and powerful gradient-based methods. So another paper which is published, actually, which is submitted in Transport in Porous Media. It is a result of collaboration between several universities, several countries. It is about a full gradient topology optimization. If you remember that plate, so that plate was the subject of my PhD thesis. Then one of my PhD student start to consider, let's say, 5 areas and then 9 areas for gradient topology optimization. Another PhD student consider full gradient across the whole of the structure. So here you see the angle, the internal angle of each cell can be changed freely. So you can see the change in internal angle from -50 to 50. So that when it is 50, it is a classical honeycomb. When it is minus, it is an auxetic. So you see that the areas that are near to blue, they are auxetic area, and the areas which are red, they are classical areas. So here you see, here we have a combination of auxetic and non-auxetic structure together so that we can represent a very good noise reduction performance for the structure. So what is interesting here that we have some backward shift in peaks of the resonance. This is useful for aerospace application. Some people say that maybe the equivalent radiated sound power level method that we have used is not suitable for low frequency range approximation. Yeah, it is maybe true, but it can help us in fast evaluation. But for high frequency range, it is suitable. And you can see the result here. I had also some research on design of the mufflers. So mainly what I had done, I had some undergraduate students who tried to produce some muffler, try to change their geometries, let's say intake, outtake for the chamber, reduce length, to see how is the effect on their noise transmission loss. In another, one of my, I had also a couple of master students. One of them worked on the effect of the absorptive material on the reduction of the radiated noise. And we use different material, and you can see that how using the absorptive material, you can increase this, increase the sound transmission loss in higher frequency range. We had also a paper in 2020 in Applied Acoustics, which was about the design, experimental and theoretical evaluation of multi-chamber reactive silence. It is once again about the topology optimization, number of chambers, how many chambers can provide better noise reduction. It's in the design. So the last thing I should mention that we are currently actively working on one project. It is about getting inspiration from the wing of one dragonfly and developing multi-layer thin metal surfaces for vibro-acoustic application. It is a very exciting project, and we are in the last stage of this project. So I hope that you have enjoyed from the presentation. And if you have questions, I will be ready to discuss with you. I'm also very open for collaboration, working together and learning together, transferring the knowledge in any way. Thank you very much for your attention. So, okay, I wonder if you have any question. If you have any question, you can raise hand, then I can give you a chance to discuss. Okay, the first one.
Hello,
okay.
Hello, Dr. Ranjbar. Can you hear me?
Yes, yes, I hear you.
Okay, I'm Vivek from the University of Nottingham, and I'm really interested in your work because I'm also working on something similar. I'm a PhD student at the School of Computer Science in the university, and I have to say that was an excellent presentation, and I had missed many of the research works that you had done, and I'm going to look at all your papers. I had a few questions from the presentation. When you applied genetic algorithm and Tabo search, were those applications on topology optimization or on auxetic materials?
Can you repeat your question, please?
You had applied genetic algorithm and Tabo search on in your research work. I just want to know, if you applied genetic algorithm to topology optimization, what was the representation you used? Because when I use it on the discrete topology optimization, I'm not able to get solutions which are smooth in shape. Do you do some kind of filtering to obtain such smooth shapes, or do you use some kind of variable? For instance, in auxetic material design, you use other variables like the radius circle and other parameters that you optimize using GA. Can you throw some light on how you use GA?
Yeah, sure. I would like to discuss. Actually, I should, at first, I see that my PhD supervisor is there, Professor Stefan Marvel. So let's say hello to him. I should be very careful now to talk. Actually, to talk. So, very interesting. Actually, you know, for normal structure, actually, you can have a smooth design, I mean, of topology. It depends on the type of the place that you are considering for the topology modification point. For Auxetic, we actually also it is possible we will have the smooth design. It depends on the number of layers, the type of element that you are considering. Okay, actually, if you have more in-depth question, please let's have to a special meeting. Then I can explain for you. Actually, I see no problem.
Okay.
Regarding the application of methods and in their topology design.
Okay, I'll email you and set up a meeting.
So, surely we can have a meeting. You are welcome. So also, so I have a question from. So let's say hello to Lionel. Thank you, Lionel, for attending from Airbus. So it was nice to have you here. So another question from Ankur. Type of excitation is decided in the experiment like harmonic. Yes. Actually, at first, you know, it was a very you know, at first we consider the harmonic excitation over the local and let's say whole of the surface. Then providing this type of excitation is easy because you just using a harmonic shaker, and then you can excite the structure. For the next paper, another paper, actually, we use different type of noise. And different type of noise can be applied actually in the experiment to see how is the performance. I mean, different type of excitation is very important to understand because it can represent a different application, whether it, for example, it is an aerospace application, or an automotive application, whether it is a train, railway application, which application. So we have different excitation. That was that I really like that paper written by Ali in 2020, which showed that actually the effect of the excitation on the noise propagation. It is quite informative, I mean, from the industrial point of view. Good. Any other question? If you have question, you can raise your hand. Good. I think. So, I wonder if Stefan like to advise us something regarding the vibro-acoustic. Good. Great. So I hope that you have enjoyed from the meeting, and And if you don't have any other question, I would like to close the session. Thank you for all of you to attending. I hope that we can establish collaboration if I can. So if you have any question, please don't hesitate to contact me so that we can work together in the future. So Zu, I am done with the presentation.
Yes, that was great. Thank you very much for joining us. It was very welcome, and it looks as though, obviously, from the chat that we've had, that people have really enjoyed it. So thank you very much for joining, Yukan, and thank you very much for your time.
You're welcome. You're welcome. So if there is no other question, then we can close the meeting.
Yes, thank you very much, Mustafa.
Yes. Yeah, Professor Marburg is there. Yeah, I wonder. Yeah, you're welcome, Ashraf. And I learned the basic from you, and I wonder if I was a good student for you or not, but I tried my best.
I know.
Thanks very much, Mustafa. If you would like to close the meeting, it's just the red button at the bottom, but that's very much appreciated. Okay. Thank you very much for your time today.
You're welcome. You're welcome. Take care. Take care.
Thank you.
Thanks.